All right, welcome back again, everybody. Today we're moving on to the last section of chapter 12. That's section 12.6. And today we're going to be talking about cylinders and quadric surfaces. Let me go ahead and pull up the slides and we will get started. This one shouldn't be as long as the last one. The section on planes, lines, and planes is just pretty long. There's just so much content. Yeah, all right, so here's the overview. We're going to do a very quick half-minute review of conic sections, just like the basic forms of the standard forms, the basic structure of the standard forms. Then we'll talk about what cylinders are, and then quadric surfaces, and then some helpful Mathematica commands at the very end. Right, so yeah, there we go. So just a very quick review of like the general form, or I should say the general forms and standard forms of conic sections. Parabolas, the ones you know and love, y equals x squared, x equals y squared, and then oftentimes you'll have a shift involved. That's what that is. Circles, classic, x squared plus y squared equals some number, some radius. Ellipses have this standard form. And the general form of an ellipse looks like this. So a lot of times this is a little more handy. We'll see why in just a few minutes here. And then for hyperbolas, it's similar to the structure of an ellipse. The only difference is that the sign here is negative instead of positive, right? So these are the structures we're going to see a lot. So it's good to kind of have both structures in mind. Maybe an intuitive way of thinking about it is that an ellipse is basically a scaled circle, right? So if you think of an ellipse, it's basically like taking a circle and squishing it or stretching it in one or both dimensions, and that's how you get an ellipse. An ellipse is a similar idea, except now you got this subtraction here. Oh, just 1 second, 1 second. Okay, so that's just a quick review. We're going to use all of these things in particular, just to get rough ideas of the types of objects that we are looking at. That's why I wanted to quickly go over them. All right, so first, what is a cylinder? So a cylinder is a surface that consists of all lines that we call rulings that are parallel to some given line and pass through a given plane curve. So one of the reasons we have this definition is because you might be thinking of a cylinder as just a classic circular cylinder like a can, right? So not every cylinder is circular. You can have cylinders of all types. The main thing that defines a cylinder is that you basically have a line, and then you have a whole bunch of other lines that are parallel to that line called rulings, and those other parallel lines pass through some given planar curve. So easy enough. So like for a circular cylinder, it's very simple, right? You basically have, let me see here. Like, okay, here's a line. Oops. So here's a line. And then if I draw a circle at the base of it, pretend that's in the middle. Actually, I can move it into the middle. There we go. Then what is a circular cylinder? It's basically just a whole bunch of lines passing through that circle that are all parallel to that line in the middle, right? That's the idea. Okay, so with that idea in mind, I want you to kind of ponder this one on your own, and then we're going to do it together. So see if you could sketch a graph of the surface z equals x squared. Oops, z equals x squared. And one thing I want you to keep in mind is that right now we're working in R3. All right, so ponder this for just a second. What do you think this graph would look like? Right, now give yourself some feedback. Say out loud what you think this surface in three-dimensional space will look like. Right. Now, if you want if you want a fun challenge, see if you can sketch it. See if you can sketch this surface by hand. See what you get. All right, here we go. So what does this surface look like? Well, one thing I notice right off the bat is that y is a free variable. So y, or this, whatever this thing is, it's going to be infinite in the y direction. But there's a relationship between the z and the x coordinates of this surface, namely z is equal to x squared. So this is what we call a parabolic cylinder. And you can kind of see these cross sections right in here. They're called traces. We're going to look at them in just a minute. This right here is basically the parabola z equals x squared. But because y is a free variable, you're going to have parabolas infinitely along the y-axis. So y can be any real number. Y equals k give you cross sections, like I was just showing you here. Here's a cross section, here's a cross section, here's a cross section. And every one of those cross sections is a parabola. That's the idea. So that is a parabolic cylinder, right? Not a circular cylinder, it's a parabolic cylinder. Okay. This one is a circular cylinder. So circular cylinders we've already seen. Geez, I forget. I think we saw one of them in section 12.1, 12.1, can't remember. But circular cylinders are similar, but now the shape that the parallel lines are passing through is a circle, just like I said a few minutes ago, right? This is the circle here is a circle of radius 1. It's centered at the origin, but z is a free variable, so you get an infinitely tall circular cylinder with radius 1, and the axis is the z-axis. You could also look at a cylinder like so. So in this case, this structure is still circular. This is one of the reasons that I wanted to do that very quick refresher of the formulas for the conics. This is still a circle in 2 dimensions, right? Except now the circle is in the YZ plane. And here, X is a free variable. So instead of it looking like this, it looks like it's turned on its side. And if you were to look at this cross section here, you'll see this circle. And it's just a whole bunch of those, like so. So that's a circular cylinder. All right, that's it for cylinders. Now let's talk about quadric surfaces. And this looks super duper complicated, but it's not as complicated as it looks. A quadric surface is the graph of a second degree equation in 3 variables. We'll say they're x, y, and z. And the most general such equation for a quadric surface is this. Whew. This is the most general form. You can kind of see the structure here. X squared, y squared, z squared, each with a coefficient. The xy terms, the yz terms, the xz terms, each with a coefficient. Then the x, y, and z terms, each with a coefficient. And then the constant term. And again, those coefficients, a, b, c, d, e, f, g, h, i, j, can be any scalars, any real numbers, or complex numbers if you want to work with complex numbers. Yeah, all those capital letters are constants. However, if you adjust things, excuse me, by translation or rotation, you can simplify this into one of 2 forms, either something that looks like this or something that looks like this, which is nice. So beyond that, because again, like what is the intuition here? This is just a bunch of numbers and equations, and we want to have some real idea of what we're talking about, right? So more intuitively, you can think of quadric surfaces as 3-dimensional counterparts of the conic sections. So think about an ellipse, a 3-dimensional ellipse, or a 3-dimensional parabola or 3-dimensional hyperbola, that kind of thing. We basically want to look at what these objects are when we have extra dimensions. So in order to see these, this is where traces or cross sections really, really come in handy. So if we're given the graph of a surface in R3, the curves of intersection of the graph with planes that are parallel to the coordinate planes are called traces. So cross sections is maybe a little more of an intuitive way of describing these. Literally, just imagine you had some 3-dimensional shape and you chopped it. And then you looked at what you got when you chopped it. So if you ever like cut vegetables or something like that, if you take a cucumber and you cut it and then you look at the edge, you get a cross section, right? And you could keep cutting that cucumber into like little slivers. And at each one of those faces, you have a cross section of the cucumber and you can see what it looks like. If you could put all of those cross sections back together, you could see exactly what the cucumber looks like, right? Same thing with other 3-dimensional objects. That's what the traces are, all right? Yeah, that's kind of what I'm saying here as well. Cross sections just help us visualize a surface by isolating the surface's behavior in a given plane. If you got enough of these cross sections, you can get a good picture of what the surface looks like. Right, so let's try this one. Use traces to sketch the quadric surface with this equation. And what I want you to do for this one is to actually just kind of ponder what you think this could look like. So think about the forms of the conic sections and try to figure out, or try to see if you could figure out what this three-dimensional shape looks like. Right. Now say something out loud to yourself. Try to describe it. It doesn't have to be perfect, doesn't have to be exact. This is just to get your brain to hear what you're thinking. Right. And now let's do this one together. So what we're going to do is we're going to basically start plugging in some numbers for x and y and z and seeing the resulting cross section that we get. That's the idea. So if we plug in z equals 0, for example, this term disappears, and then what we get is this. Well, that's an ellipse. That's the shape of an ellipse, right? So what that means is when z is equal to 0, this is an ellipse. So the cross section is elliptical when z is equal to 0. Let's plug in some other values of z. If you plug in some other values of z, say like k, where k varies, then what you get is you get another ellipse. So remember that the structure of an ellipse looks like this, and then this, or I should say, you could always normalize this so that it's equal to 1, and then what you get is like a scaled x squared term, a scaled y squared term, and then 1. Here k is a constant, so this is just some number. So no matter what you do, whatever these k values, you're always going to get an ellipse as long as the plane, the way that you're slicing, is parallel to the xy plane. Every time you do that, you get an ellipse, as long as k squared is less than 4. So if k squared is greater than 4, then you got problems. That's not going to work because you can't. The sum of two squares cannot be negative. So that means there are boundaries. There are boundaries to this object. Okay, now let's do some other traces. So play the same game, run the same algorithm, think of the same idea. So instead of setting z equal to some values, try setting x equal to some values. If you set x equal to some values, you get a structure that looks like this. And once again, you could normalize this so that this is equal to 1. Just divide by 1 minus k squared, and you'll get a scaled y squared, a scaled z squared equals 1. That's an ellipse. That's an ellipse. Just got to make sure k is between -1 and 1. Same thing here. So do the same thing with the y's, and you're going to get another ellipse. So what this is saying is that no matter which way you chop this thing, you keep getting ellipses, right? The ellipses are slightly different in size, right? They're squished slightly differently, but they're still ellipses. And that's why this thing is called an ellipsoid. It's kind of like a football. It's kind of like the shape of a football. Or I should say an American football. It's the shape of an American football, or better yet, like a rugby ball. That's kind of what it looks like. It's called an ellipsoid because all of its traces, all of its cross sections are ellipses. You can kind of see a couple here in the picture. Do it here, right? Could also do it, see, I did that, I did that. Oh yeah, I could also do it like here. So this is basically the three-dimensional generalization of a two-dimensional ellipse. There you go. Uh, Maybe interestingly, the planet Earth is an example of an ellipsoid. A lot of times people say the Earth is a ball, but it's not a perfect sphere. It's actually more of an ellipsoid because of the spin. So it's actually flatter at the poles than it is at the equator because the Earth is spinning around. So it takes what would be a sphere and kind of smushes it a tiny bit. All right, try this one. So here's another one that I want you to kind of try on your own. And now that we've played around with these cross sections, do this one on your own and we'll do it together in a second here. So think about what you would do first, right? Now say something out loud. What do you want to start with? Right, now try to work it out. plug in some numbers, think about the traces, think about the cross sections you get, and then let's put all the pieces together and see what we actually have. All right, here we go. So, well, let me see. What do I start with? X's. So I mess with the X's first. So if you set X equal to 0, you get Z equals Y squared. That's a parabola. That's a parabola. So in the YZ plane, you got a parabola. Uh, and in fact, if you set X equal to other numbers, if you set X equal to, geez, any real numbers, 1, 2, 3, negative pi, negative E, whatever, this is going to become a number, and you're going to get Z equals a number plus Y squared. That's a parabola that's been shifted up or down. So the traces or the cross sections in X give you parabolas. Do the same thing with a Y. If you change Y to different numbers, you still get a parabola. So parabolic cross sections. So in two of these dimensions, we're getting parabolas. If we set Z equal to a number, we get something that looks like this, and that's an ellipse, right? Just like we saw before, again, you could normalize this, divide everything by k, and you're going to get a squished circle, which is an ellipse. So in 2 dimensions, we've got parabolas, and then in the last dimension, we've got ellipses. And this is why we have what's called an elliptic paraboloid, pictured right here. So these traces are parabolas, these traces are parabolas, but these traces are ellipses. So it's like a natural 3-dimensional generalization of a parabola. It's what you get when you take a parabola and twist it around an axis, but then also squeeze the result a little bit. And that's what this thing is. Right. Okay. How about this one? So this is another one I want you to try. This one's a little bit funky, but a little bit fun too. So think about this one. How would you start this one? What do you think it's going to look like? Right. Okay, now say something out loud to your partner, your friend, whoever you want, yourself, your foot, a rubber duck. Okay, and now mess around with some traces. Plug in different values for X, Y, and Z and see what shapes you get. And then we'll do it together right now. Okay, so let's look at some traces. So there's this really nice visual from the book. If you set X equal to different numbers, you get parabolic traces. In this case, they're all kind of smushed together. Remember, the traces are in different planes. So these cross sections are literally like the cucumber example, right? The cross sections are not in a single plane. This is like taking all those cross sections and like smushing them just so that we can see what it looks like. So if X is equal to K, you get these shifted parabolas. If Y is equal to K, you get these shifted parabolas, but now they're pointing or they're opening downward, right? So a little bit different. And then where it gets interesting is if you start setting Z equal to K, you get these hyperbolas. And again, that makes sense if you look at the equation here, right? If Z is equal to like 7, well, again, you can normalize this. You can divide both sides by 7, and you're going to get some squishy y squared minus x squared equals 1, which is a hyperbola, right? It's a hyperbola. So if you look at this thing from one side, you get parabolas. If you look at it from this side, you get parabolas that are down. And then if you look at it from this side, you get hyperbolas. Now let's look at it in 3D. So sometimes these 2D pictures can make it harder to see what's going on. So this is really what the cross sections look like. Right here. And again, just like that cucumber example, this is what you would get if you sliced it. Oops. Here, here, here. But then here you're going to get this, this, this. Then if I look at it down, if I look at it from the top down, I see all these hyperbolas and then this little degenerate conic section here, the X, right? And then like that, right? And now if you put all of this information together, you can see that we get this. And this surface is what is called a hyperbolic paraboloid, or a saddle, because it is quite literally the shape of a saddle. So if you've ever seen a saddle on a horse or some other kind of animal, it is in the shape of a hyperbolic paraboloid. So giddy up. Now you know how to design saddles. Maybe if you're really into that, you could find like the optimal shape of the saddle, which people have. So people have figured out what is the optimal shape of the saddle. In other words, like what coefficients do we need to apply here to make the saddle the perfect shape? Actually kind of makes me wonder if you could I bet this is you could do this. You could scan a horse's back with like a laser scanner and then basically figure out what would be the optimal coefficients for this, and then you could figure out what is the optimal saddle that would fit the horse the best. Of course, there's going to be all sorts of perturbations, right? That's one thing. This is an idealized surface, so you're going to have some sort of perturbations from the actual idealized saddle shape, because it's not like this is what the back of a horse looks like, right? So there's going to be some alterations you'll have to do too. Okay. um, Okay, how about this one? So, same kind of thing. This one, I just want you to ponder it for a minute and then we'll look at it together. The game is the same. You're basically just kind of asking yourself, what do I get when I start chopping this thing in different places? Set x equal to some numbers, set y equal to some numbers, set z equal to some numbers. What do you get? All right, now let's go through this one together. Um, so if you start setting z equal to some numbers, what you get is an ellipse. There's that ellipse again, right? So again, if z is equal to 0, you get the equation of an ellipse. So if I start chopping horizontally, I get ellipses. If I set y or x equal to some numbers, then what I get is what is this? In this case, I get a hyperbola, and in this case, I also get a hyperbola. So if you look at it from the top or the bottom, what you see are ellipses. But if I look at it from this side, or if I look at it from this side, I see hyperbolas. Oh, yeah, exactly. And so this is what we call a hyperboloid of one sheet. Hyperboloid of one sheet. There's those hyperbolas. Here they are again. And then you have these elliptical cross sections too. One cool thing about this, so this is really cool. This is one of the reasons that math is so fun to me. This is actually the type of surface that you get when you hold a soap film between two closed rings. So if you've ever taken like two rings, right, and you dip them both in soap, and then you lift. Sorry, see if I can do this. Here you go. And then you dip them both in soap, and then you pull them apart. Well, you'll notice that the soap doesn't just go straight up and down like a cylinder. You can try it like in the shower or something sometime, right? What happens is the soap won't just be a straight up and down cylinder. The soap will actually curve in a little bit, and it turns out that that curve is of the form of a hyperboloid of one sheet. It's really because the soap is trying to form what we call a minimal surface. So it's actually like minimizing itself. It's one of those physical instances of a mathematical optimization. Cool stuff. All right, now, as you could imagine, there are a whole bunch of these different things, and there's all sorts of ways you could tweak these conic sections to get these quadric surfaces. So there's a table of several of them on page 917 in the book, so you're welcome to look at that. Uh, we're going to use the table in just a second here for a couple of these, but it's got a list of all of them. So we did ellipsoids, elliptic paraboloids, hyperbolic paraboloids, hyperboloid of one sheet. There are also, excuse me, hyperboloids of two sheets and cones. So you can have cones as well. Another interesting example. Wait, do I say this later? Don't think I do. This is actually the shape you get with going back to the soap film example. This is the shape that you get once you pull the rings too far apart and the soap film breaks into two pieces. What happens is it goes up to the top and then down to the bottom until it eventually just forms two flat films in your rings. So this is like if you were to keep pulling these rings apart it'll eventually snap into these two shapes, and then they'll eventually just settle as two flat planes. All right, so let's do this one. Let's identify and sketch the surface here to see what it could be. So this one I want you to ponder for a minute. What could this surface be? Right? Maybe take a look at the previous slide. Say something out loud to yourself. What do you think it could be? Right? Now, see if you can write down what it is. Use this table here and see if you can figure out what this is going to be. Might help to put it in standard form. Right, let's take a look. It may not be immediately apparent just looking at it because it's not in standard form, but we can put it in standard form. Wait, do I have a typo here? No, I don't. Yeah. So what I did here was I subtracted 4 to get -4 over here, and then I divided everything by -4. So let me write this here. Change this to -4, and then divide everything by -4 so that the right-hand side is normalized as a 1, right? And now you can kind of see what goes on. So if you think about the traces, if I set this equal to 0, I get a hyperbola. If I set this equal to 0, I get, well, that's not even possible. We'll see what happens there. If I set this equal to 0, then what I get is I get another hyperbola. So there's some hyperbolic behavior going on, and things are a little bit different when y is equal to 0. Almost seems like that's not gonna fly. Like y can't be equal to 0. And when you look at this, you can compare to the table, and you'll see that it's a hyperboloid of 2 sheets. So let me go back to the table for a moment, zoom in a little bit. There you go. That's the standard form. And the reason that I was having some issues with when y is equal to 0 is because when y is equal to 0, the surface does not exist, right? Like it's one of those situations where there's a gap here. There's a gap there. All right. Okay, where were we? Uh, oh, yeah. This is just kind of what I was saying. So, yeah, the surface has no trace in the xz plane because if you plug in y equals 0, the resulting equation has no solutions. Why is that the case? Well, because then what you get is you get x squared plus z squared over 2 equals -1, which is not possible. However, for k, for the size, as long as the size of k is greater than 2, you get elliptical traces, and that's where you get the hyperboloid of 2 sheets. That's the idea. Right. Now, where are we? Okay, let's do this one next. Similar thing. See if you can figure this one out. Classify the quadric surface given by this equation. Think about it on your own for a minute. Look at the structure a bit. Right. Now say something out loud about what you've observed. Anything. Right. Now see if you could work it out. See if you can write it in a standard form that will let you classify it. As a hint, I'll say there's a technique you need to use to get it into standard form, a technique we've seen before. All right, here we go. So it's not immediately apparent what it is because it's not quite in the right form. But what we can do is we can complete the square. So the issue is we have this extra x term. And yeah, we have an x squared and an x term. So the terms involving x are not merged together. Well, we can merge them together by completing the square. So rearrange things a little bit, put the terms with x in it together, add and subtract the special number. In this case, it's 9. Then you can factor it to get x minus 3 squared. That stays. And then we'll throw this to the other side and get a structure that looks like this. Right. So now, looking at it, you could think about some of the traces and see what we get. I guess I say it right here. It's an elliptic paraboloid. Yeah, again, think about it like this. If you set this equal to some number, you're going to get an ellipse that's been shifted a little bit. So, but then if you set this equal to some numbers, what you get is a parabola. And then if you set this equal to some numbers, what you get is a parabola. So in two of the dimensions, you get parabolas, and the other dimension you get an ellipse. So you end up with an elliptic paraboloid. But in this case, it's just been shifted. It's been shifted 3 units in the x direction. That's the idea. Oh, and 1 unit in the y direction. Yeah, there you go. So uh, the vertex is at 3, 1, 0, and this is what the picture looks like. Cool stuff, huh? So this is one of the reasons why I wanted to do that quick review of conic sections. You're really just trying to look for the rough structure of these things. Is it something squared plus something squared? Is it something squared minus something squared? Quadric surfaces are just kind of generalizations of those conic sections, right? All right, we're nearly done. So what's left is some helpful Mathematica commands, but just to leave you waiting, we're going to do that in activity. Yes. So most of the Mathematica commands that we're going to use, well, I shouldn't say most. Some of the Mathematica commands that we're going to use for this section are going to be, I didn't want to spend a bunch of time on them because you're going to be able to do them in activity anyway. But things like contour plot 3D. There's another one that I'll teach you which lets you display different graphics. So what we're going to be able to do in activity is look at the different traces, or I should say the contour maps, and then look at the actual 3-dimensional versions of these objects. So this will be a situation where I didn't want to take a bunch of time in the lecture because it's just so much easier when I can work in person and talk to you all about it there. But we'll do that in activity. So on that note, let's play. I'm glad this one was a little bit shorter. Again, I won't dwell since the last one was so much longer, but thank you again for watching, and I'll see you next time. Have a good one.